to attempt to tell you something about how stars form. All right, and in order to do that, I first have to tell you a little bit about the interstellar medium. And I know this is something that's a lot less familiar to many journalists and, in fact, many scientists than, cosmology, large-scale structure. It's not sort of, the sexiest thing in the world. So I'm going to start with, what is the interstellar medium and how is it related to stars? Then I'm going to try and say, why is this a problem for supercomputers? Why do we use computers to attack this problem? And then I'll end on what are the big questions and how do simulations help answer them. All right, so let's start with the first thing. What is the interstellar medium? Now, you could go and ask Google. So if you Google image search interstellar medium, the first couple pages are all these very nice, pictures and nebulae and things like that. But if you dig a little deeper, you encounter the following. This is the interstellar medium. It's worth reading. That's the text that accompanied the picture. So, you only have to go a couple pages into Google image search to find this. But actually, the amusing thing is, this part is actually what I'm actually going to talk about. How from the hydrogen oceans of deep space, condensation occurs. All right, so that's the interstellar medium. All right, now, the first real detection of the interstellar medium, the way people knew it was there, actually goes back to 1784 and William Herschel, although Herschel didn't know what he was seeing. But he probably saw something like this. All right, we don't actually know exactly which object Herschel saw, but he saw something like this, and this is what he said in German, and since I don't speak German, I helpfully looked up the translation. Here truly is a hole in heaven. All right, so Herschel saw something like that. Now, this is a very spectacular example. Okay, so. All right, so in 1784, Herschel saw something like this through his telescope and said, here truly is a hole in heaven. All right, and actually had some elaborate theological story about how this is coming from the fall of man and, original sin, and the stars themselves are burning out thanks to original sin. It's great fun. Turns out, this isn't a hole in heaven. This is actually a foreground object. This is a cloud of dust and gas in interstellar space. All right, now, we have somewhat better telescopes today than Herschel. And in particular, we have telescopes that work not just in visible light, but in the infrared. So here's this same object if you look in the infrared. All right, so here the red channel is showing you infrared, and the other channels are showing you visible light. And you see all these red dots. These are stars that are behind the cloud. All right, and you can see them in the infrared and not in visible light because although this cloud is opaque in visible light, it's transparent in the infrared. And it's transparent in the infrared, it turns out, for the same reason the sky is blue. All right, small particles are much more effective at blocking, scattering, absorbing blue light than they are red light. All right, and it doesn't matter if those small particles are air molecules in the Earth's atmosphere or dust in interstellar space. The red light penetrates this cloud, and the blue light doesn't, and that's why you see all these background stars only in the red. But of course, this is also why the sunset is red. Yes, and this is why the sunset is red too. All right, same physics, Rayleigh scattering. All right, so now you're seeing through the cloud here, but you're not seeing the cloud itself. And if you want to study the cloud itself, well, the problem is this cloud is at a temperature of around 10 Kelvin. Things that are 10 Kelvin don't emit visible light. So you need to tune to a different color. In particular, you need a radio telescope. So let's look at this cloud in radio. This is an image of the same cloud using a molecular line observation. So I know there's a chemist out there. This is the isotope C18O. All right, so this is a rare isotope of carbon monoxide. It turns out there's lots of carbon monoxide in interstellar space. It's one of the most abundant molecules. And this cloud is full of it. And like every other atom and molecule, it has certain resonant frequencies. And if you tune your telescope to the resonant frequency of this particular molecule, you see an image of this cloud. And depending on which molecule you select, you can see different parts of it. All right, so this is C18O. Here's if you tune to N2H+. same cloud, and you see different parts of it in the different molecules, and that has to do with radiative transfer effects, how the radiation propagates through the cloud. This molecule, it turns out, is good at showing you the low-density parts of it, and this molecule is good at showing you the high-density parts of it. All right, now, this is, of course, modern data, but let me back up a little and say, how did we learn about the interstellar medium? This is, what we can do with modern telescopes. All right, turns out, probably the best original detection is 1904, the first time someone saw the interstellar medium and knew what the hell they were looking at. All right, this is from a paper by 1904, and it was an interesting observation. So I like history of science a little and history of astronomy, and there's some interesting history here. So at this period, people are obsessed with binary stars and with spectroscopy. And this particular star that's mentioned there, Delta Orionis, all right, it's a binary star system, and people were observing it, and they were watching as the spectral lines formed in the atmospheres of the two stars shifted back and forth due to the orbital motions of the stars. All right, this is the Doppler effect that I'm sure Greg Laughlin talked about. All right, so these two stars were orbiting each other. The spectral lines were constantly shifting back and forth. But there was this one line, calcium, that was absolutely stationary, didn't move with the stars. What the hell could that be? Well, this author proposed we are led to the assumption that at some point in space, in the line of sight between the sun and Delta Orionis, there is a cloud which produces the absorption. All right? So there's a cloud of calcium atoms in interstellar space that are absorbing the light. All right, and evidence came pretty quickly from this point on. All right? Here are some observations from Lick Observatory. This is observations made by Barnard in 1919. All right, now, Barnard had photographic plates for the first time, or one of the first people had photographic plates, and this is a sketch of what he saw. All right? These are dark clouds. This is his artist's impression of them. And you see these bands of absorption, and it became clear to Barnard with photographic images that what he was seeing was not holes in space. It was actually foreground dark objects that were blocking background stars. All right, so Barnard figures this out, figures out that there is stuff in interstellar space. All right, and a modern view is that, in fact, these dark clouds are just sort of one phase of the interstellar medium. The interstellar medium has many phases, just like water can be a liquid, it can be a solid, it can be a vapor. The interstellar medium has many phases too. And it turns out that the majority of them, or the most common phase, is one that Eddington understood in 1926. All right, and this is Eddington's Beckerian lecture in 1926 called Diffuse Matter in Interstellar Space, and he figured out, all right, interstellar space is filled with mostly atomic hydrogen, mean density of about 1 atom per cubic centimeter, mean temperature thousands of Kelvin. All right, Eddington figured this out in 1926, which is pretty impressive considering that in 1926 you couldn't actually see any of this stuff. All right, because you can only see it with a radio telescope, and of course the radio telescope was not invented in 1926, which just goes to show Eddington was a damn smart guy. All right, he basically deduced this from general principles without ever having seen the interstellar medium. All right, now this is the most common phase, but it turns out to be not the one that's relevant for star formation. The one that's relevant for star formation is actually molecular hydrogen, H2, and the density is a factor of 100 or so higher, maybe a factor of 1,000 higher, and the temperature is like 10 Kelvin. Now, just to give you a sense, we don't have good intuitive senses of what density differences mean. All right, so the mean density is 1 particle per cubic centimeter. The average density is hundreds or thousands of particles per cubic centimeter in the molecular clouds. All right. That's a density difference of a factor of 100 to 1,000. That's about the same as the density difference between, say, air and the wall. All right? That's about a factor of 100 to 1,000 density difference between air and that wall there. All right, so in the interstellar medium, you've got this very, very diffuse medium, and then you have these rocks sitting in the middle of it. And those rocks are the things out of which stars form. All right, now I should mention that, I called this a rock. It's a density difference of a factor of 1,000. That's better than the best vacuum chamber on Earth. All right, we can't make a vacuum this good. All right, so it's empty space. But it's empty space, there's empty space and then there's empty space. This is really empty space. This is mostly empty space. All right, so today we can make a census of these different phases of the interstellar medium. All right, so if we take a Milky Way census, well, we've got stars, and you can see those in visible light, and that's a mass of about 10 to the 11 solar masses. All right, about 10 to the 11 suns. That's the stars in the Milky Way. All right, but if you want to observe the atomic hydrogen, well, you use your radio telescope, and it turns out there's about 10% of that mass in just interstellar atoms, atoms floating around in interstellar space in between the stars. All right, now if you want to look not at the atomic hydrogen, that's the diffuse stuff, but you want to look at the dense stuff out of which new stars could form, well, you have to use a different tracer. Turns out that you can't actually see the H2 molecule for reasons of quantum mechanics. Nature is cruel. All right, the H2 molecule is a terrible, terrible radiator, and you can't detect it with a radio telescope in general. All right, if you're interested, you can ask me why later. It turns out that we are screwed by quantum mechanics. So instead, you have to use a tracer, something like carbon monoxide. And this is an image you see in carbon monoxide. And when you work out how much mass there is, turns out there's about 3 billion times the mass of the sun in interstellar molecular hydrogen as traced by carbon monoxide. All right, and this carbon monoxide exists where the H2 exists. And if you're interested, you can ask me why. Why are they always mixed? All right, so that's a census of the Milky Way. Now, how do we know that these molecular clouds are associated with star formation? Well, I think the best evidence I can give you is just a picture. All right, this is a dark cloud. All right, now it's not as dramatic as the one I showed you before. And the reason is this dark cloud is significantly further away. So all of these stars you're seeing down here on the black background, these are stars that are actually in front of a dark cloud. And you can see the edge of the cloud outlined here and here. All right, so the reason you don't see this as totally black is that this cloud is pretty far from Earth. So there are a lot of stars in between us and it, whereas the one I showed you before happens to be very close to Earth, so there are very few stars between us and it. But it turns out that this is a dark cloud. In fact, it's much, much darker than and bigger than the one I showed you before. All right, so this is the visible light image. Again, you can see through it if you tune to the infrared, so let's do that. It's the same object in the infrared. These are newborn stars. All right, same up here. That's a cluster of newborn stars. All right, so that's how we know that these things make stars. Here's the original visible image. Here's the same field in the infrared. All right, some of you may have seen this image before. This is like the pillars of creation image. This is the mountains of creation, because everything needs to have of creation in it when you talk about star formation. And because NASA apparently has some very grandiose namers. All right, it's a cool picture nonetheless. All right, so that's what things look like in the infrared. Now, this is a particular cloud. I can also do this on a galactic-wide scale. All right, so this is a map of a nearby galaxy. The telephone number is up at the top there if anyone knows or cares. I can't keep track of these things. NGC, some number. All right, now what's interesting about this That's right. He thought he wasn't sure what he was looking at. Some of them were galaxies, some of them were, nebulae. Yes, that's right. All right, and we still use it today. That's right. So this is a map of this galaxy, NGC 5055, and here's the atomic gas observed through the 21 centimeter line of hydrogen. If anyone's interested, you can ask me why hydrogen emits radiation at 21 centimeters. Here's the molecular gas as traced by carbon monoxide. Here's the total. All right, you can ask, how does that correlate with where stars are forming? All right, and here's the map of the star formation. All right, now this illustrates very well. This picture and this picture are essentially identical. All right, so what this tells us is that stars are forming out of that molecular gas. All right, there's this excellent correlation between where the molecular gas is and where the star formation is occurring. And in fact, if you take this image and you divide by this image, you get basically a flat field. All right, that molecular gas is turning itself into stars at a sort of constant rate. All right, so this is the observations. Now, I don't do any of this. I don't know how to use a telescope. I'm not one of these people who had a backyard telescope. I'm utterly incompetent. I can't find anything in the sky. Where do I come into this story with my incompetence? Well, the answer is I try and figure out how the hell that turns into that. All right, so why is this a problem for supercomputers? Well, there are a couple of reasons. First of all, molecular clouds are filled with hypersonic turbulent motions. All right, when I say hypersonic, all right, I mean that the gas is flowing around at a speed of, say, 30 times the speed of sound in the cloud. All right, so things are moving not just supersonically, but way faster than the sound speed. All right, this is a regime with which we have almost no experience on Earth. Basically, the only time you get anything moving that fast on Earth is when a meteorite falls through the atmosphere or a nuclear explosion goes off. That's what it takes to make hypersonic turbulent motions. All right, and we have no good analytic theory of this. We're just hopeless at it. There are many, many physical processes that are important. We have these hypersonic gas flows. We, of course, have gravity. If you want to make stars, gravity should probably play a role. It turns out that this interstellar gas is magnetized, all right, which means that you need to worry about magnetic forces acting on the gas. And this gas is radiating. It turns out that radiative forces and radiative heating and cooling are important effects. When you see a list of things like this, you go, oh, crap. And then you turn to your computer. All right, now there's also a very large range of scales in the problem, and that's another reason you need a computer. All right, typical giant molecular cloud density, as I said, is about 100 particles per cubic centimeter. We would like to understand how this collapses to stars. Now, the mean density of the sun, does anyone know what it is, incidentally? Yes. Anyone who's not a professional astrophysicist? Huh? It's about the same as water. All right, so it turns out the sun has the same density as tap water on average. All right, now, the sun has a large range of densities. The core is a lot denser. The atmosphere is a lot less dense. But it turns out the average density is about the density of tap water. All right, which is of order this. All right, so now I know we're not supposed to do too much math, but from this to this, that's a very large number. That's a big range of scales, and that's another reason to invoke a computer. All right, and finally, you can't directly observe the process of star formation because the time it takes an individual cloud to turn from a cloud into stars is millions of years. All right, so you can't just watch the thing occur in real time. So what you get instead is a series of snapshots. Here's a cloud at one stage of evolution. Here's a cloud at another stage of evolution. Here's the star that comes out in the end. And you need to figure out how to connect up these snapshots. And that's the sort of thing computers are good at. All right, so this is why we use supercomputers. Now, I know you expressed some interest in understanding what a simulation really does, and Mike told you a little bit about that. But I'm going to take a bit of a digression, and I'm going to tell you a little bit more about what a simulation really is. All right, now, there's a little bit of math in here. Hopefully, I can make it clear despite that. All right, so I'm going to take an example that has nothing to do with astrophysics. That has to do with a totally familiar phenomenon you have all experienced, which is thermal conduction. All right, I am going to calculate what happens in a frying pan. All right, here's the equation that describes a frying pan. All right, so this is an example of the sort of equation I might want to solve on my computer. All right, this is the equation of thermal diffusion. All right, so what does this equation say? And if you don't understand the math, that's fine. You can understand intuitively what it says very easily. All right, thermal diffusion is a process that describes how temperature changes with time and space. All right, so let's say I've got my frying pan. I would like to know how the temperature at a given position changes in time. All right, that's what this big T is. That's temperature. And this is a derivative with respect to time. That's how does the temperature at this position change with time? Well, what that depends on is how thermal energy, how heat, flows through this frying pan, in or out. All right, so that's what this F is. It's the heat flux, and this is a divergence symbol. And what that says is that, all right, well, if I imagine a point to this frying pan, heat could be flowing into that point, in which case the temperature should go up, or it could be flowing out of that point, in which case the temperature should go down. That's all thermal diffusion says. All right, now, what determines that flux of heat? What determines how the heat flows? Well, that's what this equation says. It says that heat flows downhill. It flows from regions of high temperature to regions of low temperature. So if I've got high temperature here and low temperature here, the flux of heat is that way. And that's what this equation represents. And this quantity kappa is the thermal conductivity, and if you're a physicist, you could ignore the fact that I've left out the specific heat, and don't worry about that. So if I combine these two equations, I get something that looks like this. All right, so this is an equation that describes how heat flows. Now, let's say I want to solve this on my computer. All right, the basic problem I have is that this is what's called a partial differential equation. It describes how the temperature changes continuously in time, so at every moment in time between now and infinity, and continuously in position, how the temperature varies from this point to this point continuously. Now, if I wanted to store that on my computer, I have a problem, because there are an infinite number of moments between now and a second from now, and there are an infinite number of positions between here and here. And my computer, despite all the advances, does not come with an infinite amount of RAM. My computer comes with a finite amount of RAM. So how do I make this into a problem a computer can solve? Yes?
It might be worth pointing out that that equation at the bottom applies to every point in space.
Yes, it applies at every point in space and every point in time. That's right. All right, so the way I deal with this on my computer is I say, well, I can't represent continuous space, so I'm going to represent space discretely. I'm going to chop it up into a bunch of boxes. Now, this is only one way to chop up space. There are many possible ways, but this is sort of the simplest. Here's my square frying pan. Let's say it's a griddle rather than a frying pan. This is my square frying pan, and I'm going to chop my frying pan up into a bunch of little cells, little boxes. All right, and I say, I'm not going to worry about what happens on size scales smaller than the distance between these two boxes. All right, I just want to know what's the average temperature in this box, the average temperature in this box, and this box, and this box, et cetera. That's what I want my computer to figure out. This is what's called discretizing the equation. All right, now what I have to do is then come up with, this is my equation, a discrete representation of that. All right, and it turns out this is a discrete representation of that equation. All right, and you can actually mathematically show that this is a valid discrete representation. All right, and by valid, I mean that in the limit where my number of cells becomes infinite, where these cells get smaller and smaller and smaller, this discrete operation converges mathematically to the continuous operation in the original equation. All right, now what I want you to notice about this is that, all right, so this Tij is the temperature in cell ij. It's the temperature at that point in this cell. What's on the right-hand side of this equation now involves no derivatives. There's no calculus in this. This is arithmetic. All right, this just says take temperatures in cell I minus 1. Say this is my cell, here's cell I minus 1, or this one. Temperatures in cell I plus 1, Ij minus 1, and Ij plus 1. Say the 4 cells around it, and the temperature in the cell itself, and do some arithmetic on them. So this is an arithmetic representation of this differential equation. All right, now, why the hell would I do that? Well, the reason I would do that is because computers don't know from calculus. All right, but arithmetic they're really, really good at. Your computer is basically a big calculator, and it can do plus, minus, and times really fast. And this is nothing but plus, minus, and times. So this is a discrete representation of that equation. All right, now I've discretized in space. I also need to discretize in time. All right, there are an infinite number of moments, and I can't know what the temperature is at every moment in time. I need to know what it is at certain discrete intervals in time. So I'm going to take this equation. There's still a derivative here. And I'm going to have to replace this derivative with a discrete representation. All right, and here's one simple way of doing that. All right, so this equation tells me at time n plus 1 in cell I and j, well, here's how to calculate the temperature in cell ij at time n plus 1 in terms of things I know at time n in various other cells. So this is a rule that says, how do I generate the new temperature here given the old temperature? That's what this equation represents. And this is something a computer can do. All right, now the art here is that there's more than one way to discretize these equations. There are, in fact, an infinite number of ways to discretize them. And some ways are better than others. And better here means we'll get you a more accurate representation of the right answer with less computer resources. All right, so this is an economics problem. This is a problem of I've only got so much CPU time that I can afford to buy, I would like to get as close as possible to the right answer given that CPU time. Can I come up with clever ways of discretizing the equation that will get me the best possible answer as cheaply as possible? Now, it turns out that this is actually a pretty terrible discretization. All right, this is, no sensible person would discretize the equation this way, it turns out. All right, turns out that this discretization has all sorts of bad consequences. All right, but it's sort of the simplest, dumbest one you can come up with. And you can, in fact, do a simulation using this discretization. So this discretization is a rule for, given the state of this frying pan at some time, how do I calculate the state at the next time? And then the next time after that, and the next time after that. All right, so I took this discretization. I programmed a little simulation on my laptop. All right, and let's look at it. So here's a representation of the temperature in my frying pan. And initially, let's say I've applied the flame right at the center, and so it's very hot at the center, and it's cold everywhere else. I would like to know how this frying pan warms up everywhere else and cools off here as that heat flows out. All right, so here's my discrete representation, and I just am going to turn the crank. I'm going to say, given this state, evaluate this equation in every cell computer, and then do it again and again and again. All right, and here's what I get. All right, so this point cools down, other points heat up. All right, and that's a computer simulation. I ran it on this laptop. It took about 2 seconds. This is all any of us do. We have different ways of discretizing the equations. We discretize different sets of equations. But fundamentally, what we're doing is this. All right, so that's what it means to do a simulation. Now let me go back to the astrophysics. All right, this is like the stuff that's hidden under the hood. Whoops. So in star formation, we have a couple of big questions that I'm going to try and use these simulations to answer. All right, and I'm going to focus on two when this question has a sub-question. First of all, what determines stellar masses? All right, and what I mean by this is, why are stars, it turns out, about the mass of the sun? Why isn't the typical star the mass of the Earth? Or why isn't the typical star the mass of the entire Milky Way galaxy? Why do stars have the masses they do? And is there an upper limit to the masses they can have? Now, not all stars have the same mass. There are some big ones and some little ones. Can stars get arbitrarily big, or is there an upper limit? So that's question one. And question two is, what determines the rate at which stars form? What determines how quickly gas goes into stars? So I'm going to take you on a whirlwind tour through these two questions. So let's start with the first one. What determines stellar masses? All right, now, because astrophysicists have to have funky names for everything, we have a funky name for this one. It's called the IMF. All right, and we don't mean the International Monetary Fund. Ours is much cooler. It's the initial mass function. All right, and what I mean by initial mass function is, when stars are born, what's the distribution of masses? How many stars do I have between 1 and 2 solar masses? How many between 2 and 3? How many between 3 and 4? All right, now, you want to know what this is in reality, and the way you figure it out is you count. All right, here is a young star cluster, the Orion Nebula cluster, and the reason you go look at young clusters is you want to look at regions that are young enough that you don't have stars blowing up. All right, because once they blow up, they become rather difficult to count. So you go look for regions where none of the stars have blown up yet. Orion is one such region, and you just count. All right, now figuring out the mass of a star is non-trivial, and that's actually a source of error, but if you will permit me to say we can do that, you can count how many stars are there at each mass. And when you do that for Orion, you get a graph that looks like this. All right, each of these black points is the number of stars at a given mass, and this is plotted logarithmically, so this is the log of the mass. So this corresponds to the mass of the sun. All right, that's log of m over m sun is 0. That's the mass of the sun. That's 1/10 the mass of the sun. And you get a distribution that looks like this, and it actually keeps going off on this side. All right, so this is the distribution of stellar masses, and it peaks. The most common star is a little less than the mass of the sun. You know, it's maybe 0.5, 0.6 times the mass of the sun. Why is that? All right, and it turns out if you do this in many, many different regions, you basically always get the same answer. In clusters that are different in mass by a factor of 100, in clusters in our galaxy, in other galaxies, every time you do this count, you get about the same answer. Why the hell is that? All right, and here's an even trickier one. Stars, it turns out, are about the right mass to fuse hydrogen. Why is that? All right, now think about it. Suppose the typical star were the mass not of the sun, but the mass of Jupiter. Jupiter has never ignited hydrogen in its core. It can't burn hydrogen. It's not massive enough. If you left Jupiter sitting on its own for 100 billion years, it would just sit there. All right, it would be supported by electron degeneracy pressure, if you want to be really technical. It would sit there forever and ever and ever. So why does the universe know not to make things that size? Conversely, the typical star could be a lot more massive than that. It could be more massive than the stars George talked about. It could be, 1,000,000 times the mass of the sun. It would burn not just hydrogen and not just helium. It would burn every element up to the iron peak, and then it would blow up in a few million years. Why doesn't nature make that the typical outcome? All right, it turns out this question actually goes back to a debate between Eddington and Jeans. So this is part of the fun of looking at historical astronomy. It turns out that historical famous astronomers are every bit as snippy and nasty as modern ones. All right, so if you go back to the observatory in 1926, all right, so Jeans had delivered his lecture, so Eddington had delivered his lecture on diffuse matter in interstellar space. Jeans wrote a letter saying, basically, you didn't cite me. So it turns out that astronomers complaining about not being cited goes back to Eddington and Jeans, at least. All right, so Jeans says, you didn't cite me. All right, and Jeans' objection is, Jeans has worked at how interstellar gas fragments as it's collapsing, how it breaks up into pieces. And he says, well, this has to do with the mass of the stars. This has to be related to why stars have the masses they do. All right, and Eddington says, and he's got a good response. He says, well, there's nothing in your analysis, the Jeans instability, that says that stars should come out at about the size of the sun. But the size of the sun is a very special mass. Now Eddington phrased it in terms of radiation pressure because he didn't know about nuclear reactions. But we can modernize his question. And his question is, it can't be an accident that the masses of the stars come out with this very special mass. All right? There's a huge range of masses smaller than the mass of the sun where no nuclear reactions would ever take place. There's a huge range of masses bigger than the mass of the sun where nuclear reactions would run away to the iron peak immediately. There's a very narrow range of masses, only a factor of 10 or so in mass, where stars will burn hydrogen for long times and not immediately run away and still be able to burn. Yeah. Right, so what's special about iron is it's the most bound nucleus. All right, it's ash. It's the thing that you can't burn anymore and get any more energy out of it. So if you take nuclear reactions and you let them run to completion, what you end up with in the end is iron. All right, and that's, that's the ash. You can't burn it anymore. At that point, you're out of energy from nuclear reactions. All right, so stars are very special. They don't run away and burn to ash, but they ignite. And that can't be an accident. Now, nothing in interstellar space knows anything about that. All right, I told you these interstellar clouds are at temperatures of 10 Kelvin. There are no nuclear reactions going on within them. So how the hell do stars know to be at that right mass? All right, that's a deep question that Eddington asked, and Jeans didn't have a good response. But at the same time, Jeans does have a good response, and the response is, well, that's magic. That's teleology. All right. The fact that you've raised that question doesn't exempt you from having to provide a physical explanation for how we get from a cold interstellar gas cloud to a star. That must involve fragmentation. That must involve processes going on in a cold interstellar cloud. All right? You can't get out of that by magic. It's a hard problem to resolve. I'm going to try and resolve it for you. All right, so the resolution, it turns out, at least I think, and I will say that this is work in progress, the resolution, I think, has to do with the fact that stars shine. And that shining affects the temperature of the gas around them. Gas clouds are cold until a star forms within them. Once a star forms within them, that heats them up. And that heating inhibits their ability to break down into smaller and smaller pieces. That thermal feedback from stars that have formed affects the temperature of the gas, which in turn affects its ability to break up. So I think stars determine their own masses. All right? And the reason stars are at the right mass for nuclear reactions is that it's the ignition of nuclear reactions within them that determines how much they heat the gas around them, and that in turn limits their masses. All right, so here's a simulation. All right, so in all of these simulations, I am going to tell you what's under the hood, because here's our other dirty little secret in simulation world. We never include all the physics. All right, Mike wrote down these beautiful equations for you. None of us solves all of those. And the reason is because even on a modern supercomputer, it's utterly hopeless. So instead, you take your best physical guess at what processes are important, and you only include those. So what processes are included in this simulation? Hydrodynamics, gravity, and radiation. And I use a numerical method called adaptive mesh refinement. So on the left, I'm showing you the density of gas in projection, and on the right, I'm showing you the temperature in projection. So this is a simulation of a cloud collapsing to make stars. All right, and you'll see when stars start forming, as indicated by white dots, you see these little hot spots appear around them. And this cloud heats up. All right, so is this a good representation of how stars form? Well, I can ask, what's the mass distribution of the stars that came out of that simulation? All right, now here's a way of representing that mass distribution. What I'm plotting is what fraction of the stars have a mass less than a given value. So if you read off here, 1 solar mass, this is what fraction of the mass is in stars that are smaller than 1 solar mass. The gray band is the right answer, and the green line is what the simulation is giving me. So did I get it right? Well, here's how the simulation evolves in time. Oh, I got it. No, I lost it. Turns out you learn a lot when your simulation gives you the wrong answer. You learn far more than when it gives you the right answer. And what I learned here is that this cloud heated up too much, and that heating actually made the stars too massive, and that's what this green band being to the right of the gray band represents. All right, so take 2. Here's a more realistic simulation. I started not with a spherical cloud, but with a turbulent cloud. I included that hypersonic turbulence. All right, I also included something to stir up that turbulence, which is protostellar jets. The physics included includes protostellar jets. And this is the fact that when stars are born, they shoot off these streams of gas in either direction. And that stirs up the turbulence. So let's run this simulation forward. All right, that ran for about the same amount of time as the previous simulation. It formed a lot fewer stars, thanks to that turbulence stirred up. And the cloud, it turns out, is significantly colder. It heated less. So how did this do? All right, green is the old simulation, red's the new one. Again, I want to stay within the gray band. And for the most part, I do. This simulation works a lot better than that one. So I've learned it's important to include that hypersonic turbulence if you want to get the right distribution of stellar masses. All right, now, this is not a solved problem, but it's a problem on which we've made progress. Why do stars have the masses they do? And what's nice about this answer is that it tells you why nuclear reactions come into it. All right, do stars have an upper mass limit? Let's try and cram as much mass into a star as possible. All right, this is another simulation. People have tried to do this problem. The problem is stars shine very brightly, and that radiation exerts a force. And if you do the naive spherically symmetric calculation, you conclude it shouldn't be possible to form a 100 solar mass star. Is it possible? Well, it turns out that, fortunately for us, real life is not spherically symmetric. It's also not two-dimensional. All right, all the calculations people had done before were either spherically symmetric or two-dimensional. And in 2 dimensions, and this is a terrible joke, but I learned it and so I have to repeat it. In 2 dimensions, if you go like this, you asphyxiate. No one got that joke. All right. Took a moment. All right. Fair enough. You are correct, sir. So here's a simulation of what happens if you do this in 3D. All right, so what I'm showing you is a collapsing cloud. All these panels are showing density, but from different perspectives. All right, these are zoom-ins on the bottom. On the top is the long view. All right, and I'm showing you face on and edge on. And you see these bubbles of radiation being blown. That's the radiation forcing the gas away. All right, you'll notice the flow doesn't stop. The stars keep gaining mass. All right, and if I run this simulation long enough, all the gas will eventually go onto those stars. Now, I stopped at this point because I'd blown my computer budget for the year. All right, But I accreted most of the mass onto these stars. So is there an upper mass limit? Not as far as we can tell. Now, observationally, you can say, is this scenario right? And you can say, well, here's the disk around these stars that formed in that simulation. Can I look for something like this? And the answer is, not with current telescopes, but with ones under construction. So a prediction of this model is that disks like this should be around forming massive stars. You can look for that with this. This is the Atacama Large Millimeter Array. It's a telescope under construction in Chile. All right. And you should be able to see this sort of disk. So the final stage in simulations is often, what the hell would this look like? And that's a simulation by itself. You take the output of your simulation, and you do another simulation to figure out what the hell it would look like. So I took the output of that simulation, and I did another simulation. Here's what it would look like to ALMA. And this is an observation in, the chemist should be happy again, the 220.7472 gigahertz line of methyl cyanide. Let me mention, I never took a chemistry course past high school. I hated chemistry. I've had to learn so much of it. Methyl cyanide, it turns out, is a good tracer of protostellar disks. That's what this thing should look like. All right, so how do you test, is this simulation giving you the right answer? Well, you look and see, is there something like that in the sky with ALMA? If you see it, I got it. If not, I'm hosed. Here's just a simulation of how it would look as a function of velocity. And the nice thing about an observation in a molecular line is that you can dice the cube by how fast things are moving. You can tell the velocity as well as the brightness. All right, final thing I want to talk about, I know I'm out of time. Star formation rates. Here's another example of how a simulation can mislead you. This is a simulation by Matthew Bate. All right, and it includes hydrodynamics and gravity. And you'll notice that Matthew has excellent graphics. All right, this is a collapsing cloud. And what I'm interested in is, at what rate does this cloud turn itself into stars? All right, so it's a pretty picture. And I'm just going to count up how much mass goes into stars as a function of time. All right, and the physics that's included is very simple. It's just hydrodynamics and gravity. The simplest thing you can do and still get stars to form. All right, and in the interest of time, I'm not going to let you watch the entire movie, cool as it is. All right, now it turns out that simulation, as cool as it looks, is totally wrong. So here's a plot of something I showed you before. All right, so I showed you this map of where the molecular gas is in a galaxy, and I showed you this map of the star formation. And you can ask, for a given amount of molecular gas, that's what's on the x-axis, how much star formation do I get? What's the conversion between molecular gas and star formation? That's what these contours represent. That's the observations. The simulation I just showed you is way the hell up here. It forms stars about a factor of 100 too fast. It's too efficient. All the stars there form a gravitationally bound star cluster, but the typical star doesn't form in a gravitationally bound cluster. The sun is not part of a cluster now. Most stars do not form in gravitationally bound clusters. So what went wrong? Well, and this is the last secret of simulations, is we never have in enough physics. There's always something we're missing. So here's a nearly identical simulation, but one where we include a bit more physics. And this is work done by Peng Wang and Tom Abel. What's included here is gravity, protostellar jets, and they've put in magnetic fields. All right, nearly identical to the Bate simulation I showed you before, but now you'll see that when stars start forming, they shoot off these jets of material that push gas away. All right, and you see these long jets of gas. And those jets of gas, because there's a magnetic field, are able to entrain to grab other blobs of gas and drag that stuff around. The net effect is that this simulation forms stars about a factor of 100 slower than the one I showed you before. This simulation agrees with the observed star formation rate, whereas the one I showed you before didn't. So that's the final thing I want to say to you, is that take all our simulations with a grain of salt, because we've never put in all the necessary physics. We are very far from being able to do that. In your entire career, you will never see any scientist come to you and honestly say, I put in all the necessary physics. All right, we're always approximating. Simulations are an approximation tool. They're not reality. And every time we put in more physics, we discover something new. It's all provisional. That's the way it is with simulations. I'll end there. Well, no, so it's not a survival thing because, and that's why we distinguish the initial mass function from the present day mass function. All right, so the initial mass function is just what gets formed, not what survives. Now, it turns out that big things do have very short lifetimes, and they blow up. Small things, in fact, have infinite lifetimes. All right? I mean, Jupiter will sit there forever and ever and ever, and nothing will ever happen to it. All right, so there is a selection in transforming from the initial mass function to the mass distribution of what's around today. But when we talk about the initial mass function, we're explicitly taking that part of out of the equation by looking at things that are young enough that no evolutionary effects have happened. I saw.
So, I feel like this is maybe kind of a dense question, but if it's so hard to get supercomputer time and it takes so long to run the simulations and it's expensive and everything, and you know that there are things like magnetic fields or like jets that we see in the actual world, why don't you wait until you can run long simulations?
Well, okay. I mean, there are a number of reasons. Oh yeah, sorry. I'm supposed to repeat the question. The question is, given that you can't put in everything and it's so hard to get supercomputer time, why bother? Why run the simulation when it's incomplete?
That wasn't exactly what I meant.
Okay, sorry, I sharpened it a little. I made it snarkier than it was. I apologize. No, but it's a fair question. I mean, so why not wait until we can put in the all the necessary physics? All right, and the answer is, why do it iteratively? All right, and there are a couple of reasons. All right, well, and the first is, and I think this quote came up before, the point of computing is insight, not numbers. All right. Our goal is to understand what's going on. Our goal is that we understand physics, not that computers understand physics. And the problem with the kitchen sink approach of putting everything in and just waiting until you can put everything in is that, all right, maybe you get the right answer, but you have no idea how you got it. You didn't understand it at all. Whereas the iterative approach lets you understand, all right, well, when I include this effect, what happens? All right, so that's part of it. A second part of it is that if you try and put in everything at once, you are almost certain to do it wrong. All right, as I said, there's something of an art here. Getting something that'll actually run stably and that will give you the right answer is not at all trivial. And if you try and do it all at once, you're very, very likely to screw it up. All right, and the third thing is that for some problems, that's simply never going to be practical within our lifetimes. All right, the time to put in all the necessary physics at all the resolution you'd want, I mean, yes, computers are growing in power exponentially, but it's still not going to happen. You can't simulate the whole universe. And so the alternative to doing nothing is, the alternative to running a simulation that's partial is not doing anything and trying to work it out on pencil and paper, and that's much, much worse. All right, so it's the best you can do, and it gets you more insight than sitting on your hands. All right, questions? Yes?
So your simulations appear to get the right distribution of stellar masses when you included turbulence and magnetic fields.
I didn't actually put in magnetic fields. I put in prostellar jets, but not magnetic fields, yeah.
So my question is the value of the turbulence and the value of the magnetic field you put in, are they consistent with observations? Are they reasonable?
Yeah, so the turbulence that I put into that simulation for getting the IMF right was, yes, it was chosen to match observation. And similarly for the simulation, the last one I showed with the magnetic fields were chosen to match observations, at least roughly. So yes, you have to put in something reasonable.
So I'm not sure I understand what the origin of the magnetic fields are at the end.
Okay.
What, can you explain that?
Yeah, so where do the magnetic fields come from? All right, well, all right, so the short answer is that interstellar gas, the question was, where do the magnetic fields come from? All right, and the answer to that is that, first of all, interstellar gas is not totally neutral. It turns out it's a plasma. All right, and the reason is that interstellar space is filled with X-rays and ultraviolet photons and things like that produce ionization. All right, so in this room, the air is extremely neutral. There are almost no charged particles in the air. But if I go to interstellar space, there are lots of charged particles, and depending on the density and the conditions, there can be one charged particle per 1,000 neutral particles, or one charged particle per 10 million neutral particles, or even less. But you don't need very many charged particles, it turns out, to sustain a current. All right, as long as you've got free charges, like you do in a metal, currents can flow. And as long as currents can flow, currents generate magnetic fields. It is a general case that anytime you've got a partially ionized or fully ionized fluid, currents will flow through it and will produce magnetic fields. All right, so that's sort of why there can be a magnetic field in interstellar space, is because there are currents that generate it. Now, the origin of cosmic magnetic fields, where did the first magnetic fields come from? No one's totally sure. So, I mean, the best answer is probably that it's something like a dynamo, like what operates in the core of the Earth and generates the Earth's magnetic field, operating in the first galaxies and the disks around the first black holes and the first stars. No one completely understands. But that dynamo process generates magnetic fields, we think, in the same way that it happens in the center of the Earth. And those magnetic fields are then sustained by the currents in interstellar space. Does that answer your question?
Yes.
Yes.
Has anybody mapped the distribution of molecular clouds across the universe, or
Okay, so the question is, has anyone mapped the distribution of interstellar clouds or simulated it? All right, and the answer is, in nearby galaxies, yes. I'll go back to this picture I showed you, way back towards the beginning. There we go. This is a map of molecular clouds in this particular galaxy. Now, this is a fairly low resolution map, and for some galaxies, much higher resolution maps are available. So, yes, we have maps of where the molecular clouds are and what their properties are in nearby galaxies. In the Milky Way, we have maps too. Those are a bit harder to interpret because you don't know how far away the thing you're looking at is. So you see a cloud in that direction, but how do I tell if that cloud is close to me and a little cloud or far away and a big cloud? All right, that's a hard problem for the Milky Way. It doesn't apply, not a problem in distant galaxies. Now, beyond that, in the more distant universe, well, we have very limited maps, and in fact, making those maps is one of the things the ALMA telescope is supposed to do. It's supposed to map the molecular clouds in the distant universe. All right, right now we don't have a way to detect them. Yes?
I've seen pictures, and there was even a presentation at the HiPACC Berkeley workshop a year ago, a brief presentation where people have been simulating stars that supposedly have 30 to 50,000 solar masses. And, are those like really primitive stars that were early on, or what's going on? Can a star have a mass that is 30 to 50,000?
Good question, and the honest answer is we don't really know. All right, so let me say that, all right, from the simulations I've done so far, there's no reason it's physically impossible to form such a star, but that doesn't mean it actually happens in nature. All right, sorry, so I should repeat the question. People have been simulating stars with masses of 30 or 50,000 times the mass of the sun. Can those stars exist? All right, and the answer is they don't seem to be forbidden by any process, but that doesn't mean they actually occur in nature. All right, what would require, so if you let me set up a 50,000 solar mass cloud that was perfectly symmetric, and I could let it collapse under its own gravity, if you let me engineer it, there's no reason I couldn't make such a big star. All right, but does nature actually provide the initial conditions that give rise to that? Almost certainly not in our galaxy. Now, maybe in the early universe, you can get conditions that look like that. I'd be skeptical, but there are people in this room probably more qualified than I am to comment on that, like Mike. I would be skeptical. In the present day universe, almost certainly not. You?
There's another part of the answer is you have to distinguish whether you could, in principle, make such an object, and whether if it was made, would it actually survive.
Yes.
So Mars addressed the question of, can you form very massive stars? He finds that there, is not an impediment to forming 100 or 200 or 300 stars. But that doesn't mean that if it forms, it's actually going to sit there and move for really years. A lot of work on the possibility that even if you create these very massive stars, they'll spontaneously kind of blow themselves apart and shed mass. And that may actually be the process that limits the masses of the stars. Not this formation physics, but that it's just not a stable configuration that can survive for a long time.
Yeah, and I completely agree with that.
That's also not a solved problem.
Yeah.
I think that
Yeah.
Well,
Yes.
you can build on a computer, of course, a 50,000 solar mass star, and it will sit there radiating at the maximum rate of radiating in limit for about 2 million years, and it'll go extinct. So stars like that, if you could make them, will make black holes.
Well, okay. I mean, but I think Elliot is asking, would it be stable even for 2 million years? It's not at all obvious that it would be. I mean, yes, you can tell like the MESA code, run me a 50,000 solar mass star, but the MESA code won't check if it's subject to like photon bubble instability or something like that that's going to blow it up. So I think that's the question Elliot's raising, and I don't think we know the answer.
I'm just saying it's spherically symmetric. That's what's using it.
Right, but
And then in the perfect world, perfectly spherically symmetric star, this is just a big parent still.
I agree, but yeah, real life isn't spherically symmetric, and it might be unstable once you relax that.
Short answer is
Yeah.
there's no evidence of stars more massive than where everybody debates 100 or 300 solar masses.
Yeah. Yeah. Yes.
Was the real distribution of stellar masses in the early universe different from what it is today?
So the question is, was the distribution of stellar masses in the early universe different than what it is today? I think so. So the observational answer is we really don't know yet because we have no good observational evidence for what the masses of these stars were. The theoretical answer is probably yes, and I think that's probably the right answer. That, all right, so what controls how stars break up, how gas clouds fragment, is their temperatures. All right, and that's determined by the heating and cooling processes that occur in the gas, how the gas interacts with radiation, how it emits radiation, how it absorbs radiation. Now, it turns out that most of that interaction with radiation is done not by the hydrogen. Hydrogen is terrible at interacting with radiation. It's done by heavier elements. It's done by metals, using the astronomer's definition of a metal, that anything heavier than hydrogen and helium is a metal. So, oxygen is a metal, nitrogen is a metal, et cetera. So in the early universe, you didn't have metals, or you had almost no metals. And so the interaction of the radiation and gas was almost certainly different. How that translates into a different stellar mass spectrum is still a problem that I'd say is not totally solved. If you ask Mike, he'll say that yes, the stars were more massive in the early universe, and I think that's probably the right answer. But I don't think we have hard observational evidence one way or another. All right.
One of the reasons why we're working so hard to go from first stars to first galaxies to first observable galaxies is so that we can address that question by inference.
Okay, so maybe, I guess, one last question, or?
One last.
All right. No last question. Everyone wants to get to the snacks. All right, we're done.